Hello and welcome to my new series on calculus from scratch, where I'm going to start building up calculus from scratch, and hopefully it will teach you a little bit more about the intuition behind calculus and why it really works. Okay, so the whole idea of calculus came from originally just these. Well, if we first look at a straight line graph, so this is our y, this is our x, that's not our x, this is our x, we get a line. There's one specific aspect that we're looking for here, and it's the gradient. And what is this gradient? The gradient is basically how steep it is. You can think of it like the gradient of a hill is how steep it is. But you can mathematically describe this number, and obviously this is in your format. When you see y equals mx plus c, then m is your gradient. It describes how y changes with x. It's a number that describes the change of the graph, not just one specific point. So it can be very useful in real life applications, which we'll get into in another video, not now, but yeah. So let's have a look at how changing the gradient can affect the line. Right, so here I've just set up a Desmos graph, which is going to help us to see what changing this gradient looks like and see how it's described. So if the gradient's really positive, it's really steep, you know, like imagine it as a hill, you know, this is going to take effort to get up, you know, that's if it's very positive. And then if it gets less and less positive, it gets less steep, less steep, less steep, until eventually you get to 0-ish, yeah. And then at 0, it's completely flat, the line's completely flat. Then behind this, and you get negatives, and it starts going downwards instead. Yeah, so you can see basically what the gradient means and how it's mathematically described now, and what the positive, negatives, and zeros mean. It's about how the function changes. Because you can also think, like, if you budge x a little bit, you can think of this as how much y is going to grow, how much it's going to get taller by, essentially. In which way it's going to move as well, because then obviously if it's negative, if you go across 1x, then you go down by what is it? Negative 4y here. Cool. Back on our notes page, we now need to ask ourselves a question. All that's, you know, good, but how do we calculate this? You know, like, you can have it given and say, draw this, but how would you, given a line, how would you calculate that? Well, this is how. You need to first think, well, you know, it's about the change in the upwards direction divided by the change in the lower direction. So I think it's kind of obvious where that comes from. Yeah, this symbol, delta, is Greek. It means change. So yeah, I think it's kind of obvious where this comes from, but in case it's not, you can think of it as, yeah, this whole direction thing. Think of hills, really, that's what I do. Yeah, it's for every bit you've moved up, how much have you moved along? Obviously, if you've moved up a lot for not that much along, the gradient's going to be huge, yeah? And then obviously when you get negatives and everything, the other way around and all that. But yeah, think of it as hills and how much you've moved up and across. That's what this equation basically describes. But let's put this in a more clear context, and let's try actually do this mathematically, because just saying the change, yeah, it's strange. So we're going to do it in terms of y2s and y1s and x2s minus x1. So what you need to do there is choose two different points on the graph. So let's say that's point 1, so this would be, you know, x1, y1, and this would be x2, y2. And then you get them points and just shove that in this formula and you get the gradient. So that's how, and then, you know, it doesn't matter which one's your x2, x1, just as long as you keep consistent with this is the set of coordinates, you know? But what about a curve? What would you do for that? Let's have a look why you can't really use this equation there. Right, so let's look at our curve then, and we're going to do this with the most basic curve we can. You know, so that's our y equals x squared, and that looks kind of like, you know, it's a parabola. Right, now this isn't exactly what it looks like, but it's a curve. You get the gist. The thing is now is the gradient isn't the same. So when you try and use and what I mean by that is this equation thinks, in quotation marks, that the two coordinates that you're getting this from, there's the same gradient there. But obviously that's not the case here, because if you choose a point down here, it's not the same as a point up here. The gradient is different on every point of this curve. So how would you find the gradient of this curve at a point? You couldn't do it using this formula. You can approximate it by, you know, drawing out these tangent lines and then getting 2 points of that and then using this formula and everything. But it's just not convenient, and it's not accurate really, because drawing that tangent line, you know, just yourself using your eyes is hard to do, and it won't be accurate. And even if you get it slightly off, it can still just give you it's not accurate, is what I'm trying to get across. Not good to do. But you can see hopefully that the gradients become more and more similar if you get these 2 points where you've drew these tangent lines. If they become really, really close, they become more and more similar until eventually they'll just be, you know, on top of each other, and it'll be the same. Remember that, because we're going to use that principle in a second when we're constructing this idea of calculus. Okay, so now to derive our first principles formula, from which we're going to get our derivative, we're going to change our idea a little bit. Instead of doing y equals yada 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 x, what we're going to do is f of x equals, we're going to use functions in order to find it, in order to find the gradient. But we're still going to use that gradient formula. So let's draw our, you know, the easiest curve again, y equals x squared. I mean, you don't really need that, but it's just the easiest curve, isn't it? So once again, this is now f of x equals x squared. It's a function of x. You can use f of x and, you know, y pretty interchangeably, but here it's kind of like, it's f of x here. Yeah. So when we get our 2 points now, what are they? This is f of x, and this is f of x plus h, and then this is x plus h. So when we put this into a formula, we get m equals, now I'm deliberately leaving a gap here, and hopefully you can see here x plus h minus x, you just get h. So do you remember when I said earlier that when these 2 points get really close, then it basically becomes equal? Well, what we're going to do is we're going to say that it gets so close that h is basically 0. And we're using h as some kind of like variable here, so we can control where it goes, what value it has. What we're doing is we're saying it's not 0, but it's going so close to 0 that it's basically 0. And that kind of sound, it leads to this sounding like it's an approximation, but it's not. Calculus is exact. So this is our formula, but do we trust this formula? Is this enough for us to go, okay, let's accept this, let's adopt this, this is our formula now. No, it's not. So let's go test it. So the first thing we're going to test it with is just a constant. Hopefully you can see that when y equals a constant, or when f of x equals a constant, you can use f of x and y pretty interchangeably. The gradient 0, hopefully, because it's flat. Yeah. So we're expecting that if we use our formula now, our new formula for finding the gradient from first principles, or finding the derivative, it's kind of almost the same thing. We're expecting to get 0. So let's put it all in our formula and see if it happens. Right, okay, so now what I'm going to do is I'm going to show this as m. Now we're going to change that later, but for now, for all purposes, it's m. Yeah. Because we're not exactly going to get a function back here, are we? So now we need to know what we're going to put into this. We're doing this as f of x equals c, so some constant. Yeah, and we're expecting 0, remember? F of x plus h, so put x plus h wherever there's an x, there isn't one, so c. So m equals the limit as h approaches 0 of c minus c divided by h. M equals the limit, and teachers want to see that limit. It's the most annoying thing ever to write, but yeah. So now this looks like it's not going to work, but it does, because it's like, it's the limit, so it's not really 0 over 0, it's just 0, because it's getting so close to 0, but it's not exactly 0. It's that niche thing again, and it can be a bit mind-boggling, but don't think about it too hard, don't stress your little head, and it'll all be okay. But yeah, this proves that this formula here does work. Our first principle formula works, so that is a 1 tick from me. Now let's test it with a line, with a straight line. Y equals mx plus c. Now here it's going to be slightly easier, because we know what we're going to expect. We've got to expect m from this, yeah? However, now obviously it's going to be f of x equals mx plus c. And that would make f of x plus h equals mx plus h plus c. Right, now it's going to look a bit weird. It's going to say m equals m, hopefully, at the end. We don't know this yet, but hopefully it will. We're just checking. Minus mx plus c, remember the bracket here, obviously. And then we're going to put that all over h. Now this is just kind of some, mathematical gymnastics now. We've got to do some algebra. Mx plus mh plus c minus mx minus c, all divided by h, equal, oh my god, limit as h goes to 0. And obviously these we're going to cancel, and you get mh divided by h equals the limit as h approaches to 0 of m, which is just m. M equals m. Right, okay, so now that gets 2 ticks. I think it works at this point. For everything we know that what we're going to get the gradient of, it's worked. So how about we now try and do it on something, use this formula on something we don't know the gradient of. I think you can guess what curve I'm going to use it on, but yeah, let's do it anyway. Right, so f of x equals x squared. F of x plus h equals x plus h squared. Okay. So let's put this into our formula and see what we get. So now I'm going to use a different notation. It's f prime of x. That means our derivative. I'll come on to explaining all that. Just take that for now. But we need to find what we get first to talk about that. Minus x squared. You know, it's just the mathematical gymnastics again. Algebraical gymnastics, that's what I'm going to call it. x2 plus 2xh plus h squared minus x squared over h. This is the boring thing. This isn't the understanding what's going on. This is just the, do maths. Which maybe you find interesting. I don't. Two x plus h over h, so they cancel, equals the limit as h goes to 0 as 2x plus h. Okay, but now, right, so that goes to 0 and we get left with 2x. F prime of x equals 2x. Right, so that's great. That's our first ever derivative. But what does that mean? What does it mean? So we've got a new function, but I suppose we always knew we were going to get a function out of the gradient of a curve when we find the gradient, because we know it changes. We know that it changes. And, functions change. So what's this saying is that for every x value we put in, if we put this into the function, we'll get the gradient of the original function, which here, f of x equals x squared. We'll get that back. So, for example, if you put, what's the gradient at x equals 2? Well, 2x, the gradient's 4. What's the gradient at x equals 8? 16, yeah? So, you use this first principle formula. Go through all of our working. Oh, Jesus, where is it? Where's our first principle formula? There. You use this to find the derivative of pretty much anything. It's just, obviously, there's certain things and rules you can derive from this that we're going to do in later videos. It's going to help, significantly, actually, especially the next one. But, yeah, you can imagine how versatile this is, especially when then it's finding gradients like this easily. And it wasn't that mathematically heavy. So, yeah, now we have to talk a bit about this notation. Yeah, so f prime of x, this is our functional notation. It looks like it's a function, f prime of x, that's what that dash is, prime. And then, you add prime, or then you can start getting numbers up there. But that's our functional notation. Basically, the reason why there's different notations here, which I'm about to introduce, is basically history. Calculus was developed through, a few hundred years from a lot of different people from all over Europe, and yeah, they all came up with their own notations, and some are just easier to use in certain contexts. Like for deriving this, it's easier to look at it as a function. But then if you're doing differential equations and things, this is easier, which you'll see eventually. But these, they're interchangeable. They both mean the derivative. dy by dx, this is pronounced. And so does x dot. They all mean the same thing. It's just which one's easier to use in the certain context. X dot you'll pretty much just see in, physics. Dy by dx and f prime of x is the one you're going to see the most. Because they're so interchangeable. They mean the same thing. It's just sometimes it's easier to use this notation as opposed to that one. So dy by dx for all, purposes, that's pretty much easier to use. It's my preferred one. I like it just because of how versatile it is, really, to be honest. But f prime of x, it's just easier to show it being derived using that notation. Right, so this formula is the fruit of our work today. The fruits of our work, and yeah, you can see how versatile it is in finding gradients, which we're gonna explore a lot more next video, where we're gonna find out how to, easily find the derivative of a polynomial, because you saw that earlier. It's, what do I call it, mathematical gymnastics to go through all of this formula, because it is a bit of a pain in the ass. No one's ever, you see a first principles formula on an exam, you start going, I can't be asked to write out limit as h goes to 0, 10 times, because they're not always going to be as easy as the examples I showed. Actually, they're pretty much never going to be that easy. But yeah, you get the gist. Please like, comment, and subscribe. You know, it really helps to do this. You know, just a little bit of motivation to keep it going. And I hope this video helped. Yeah. See you on the next one.